Our universe holds secrets that defy everything we think we know. We are setting out on a journey through 30 of the most bizarre galactic facts ever discovered, each one a revelation that will bend your mind and reshape your sense of reality. By the end, you will see the cosmos not as a silent void, but as a living, breathing arena of impossible wonders. We will confront a gravitational mystery pulling entire galaxies off course and stand at the edge of a cosmic void so empty it should not exist. What does it feel like to question the very nature of the space around you? Our cosmic journey begins with a pull we cannot see. Every galaxy in our local neighborhood, including our own Milky Way, is caught in a silent, unstoppable river. We are all moving, not just expanding with the universe, but being dragged in a very specific direction at over 2 million kilometers per hour. The destination of this galactic pilgrimage is known only as the Great Attractor, a point in the distant constellation of Centaurus that exerts a gravitational force so immense it bends the paths of entire galaxies. Yet for decades, its true nature remained one of astronomy's great frustrations because we could not look at it directly. It lies hidden behind the dense plane of our own galaxy, a region astronomers call the zone of avoidance. Imagine trying to see a distant city skyline, but a massive, foggy mountain range blocks your entire view. That is the challenge the Great Attractor presented. Our telescopes, peering through the thick dust and countless stars of the Milky Way's bulge, saw only a cosmic blind spot. What could possibly be massive enough to command such a universal flow? Early theories suggested it was a previously unknown supercluster of galaxies, a colossal knot of matter with a mass equivalent to tens of thousands of Milky Ways. But as our technology improved and we found ways to peer through the galactic fog with infrared and radio eyes, the mystery deepened. We discovered that the Great Attractor itself is merely a waypoint. The river of galaxies does not stop there. It continues flowing toward something even larger and more distant, a structure of almost unimaginable scale known as the Shapley supercluster. This suggests the Great Attractor is not the ultimate source, but perhaps a signpost in a vast, interconnected web of dark matter and galaxies, a single tug in a symphony of gravitational forces shaping the large-scale structure of our universe. It is a humbling reminder that even the motions we consider fundamental are part of a much grander and still largely hidden cosmic dance. But if the Great Attractor reveals a universe of overwhelming gravitational pull, the next discovery presents us with the exact opposite, a terrifying emptiness. Drifting through the constellation of Boötes, there exists a region of space so profoundly lonely it has earned the name the Great Nothing. The Boötes void is a near-perfect spherical chasm approximately 330 million light-years across. To grasp that scale, if you placed our Milky Way galaxy at one edge of this void, you would have to travel for over 300 million years at the speed of light before you found another galaxy on the other side. Within this staggering volume of space, astronomers have found only a handful of galaxies, perhaps 60, where according to our standard models of the universe there should be thousands. Picture our observable universe as a glittering, bustling metropolis of galaxies. Now imagine within that metropolis a single, perfectly spherical district the size of a continent that is almost completely dark and abandoned. That is the Boötes void. It is not just empty space, it is a supervoid, a cosmic desert of staggering proportions that challenges our understanding of how matter distributed itself after the Big Bang. The mystery is not just that it is empty, but how it became so empty. One leading theory suggests it is the result of smaller voids merging over billions of years, like soap bubbles combining to form one gigantic bubble in the cosmic foam. Another, more unsettling idea is that it might be evidence of a collision with a parallel universe in the distant past, a scar left on the fabric of our own cosmos. Whatever its origin, the void stands as a stark counterpoint to the crowded galactic clusters we are familiar with, a haunting reminder that the universe is not uniformly filled with light, but is instead a patchwork of brilliant cities and unimaginably vast silent deserts. This leads us to wonder what other extreme structures are woven into the fabric of space itself. From the profound silence of cosmic voids, we find a world of unimaginable opulence. Among the most dazzling discoveries in our galaxy is a planet that could be the ultimate treasure chest, a world not of rock and iron but of diamond. Orbiting the star 55 Cancri, about 40 light-years away, is a super-Earth known as 55 Cancri e. This planet is about twice the size of our own, with a mass over 8 times greater, and it completes a blistering orbit around its sun in just 18 hours. But its true nature lies beneath a possible thin layer of silicate vapor. Astronomers, analyzing the composition of its host star and the planet's immense density, concluded this world is likely composed primarily of carbon. Under the crushing pressures and scorching temperatures of its interior, that carbon would crystallize into a layer of diamond hundreds or even thousands of kilometers thick, mixed with graphite. Imagine a world where mountains are not made of stone, but are colossal, jagged peaks of pure diamond, and the ground beneath your feet is a glittering, crystalline crust. The creation of such a planet requires a very specific cosmic recipe. It must form in a star system that is exceptionally rich in carbon, far more so than our own silicon and oxygen-dominated solar system. As the planet coalesces from this carbon-dusty disk, its immense gravity creates pressures so extreme that the atomic structure of carbon is forced into the rigid, sparkling lattice of diamond. The sheer material value of such a world is beyond any human economic calculation, a fortune so vast it renders the concept of wealth meaningless. Yet the real value for science is not in its hypothetical price tag, but in the window it provides into the stunning diversity of planetary geology. It proves that the building blocks of planets can vary wildly from system to system, leading to landscapes and interiors we once considered the stuff of science fiction. This glittering world forces us to ask what other impossible-seeming materials might form the foundation of distant exoplanets. Diamonds may be forever, but a planet's home is not. Our galaxy is filled with orphans, worlds cast out from the warmth of their suns to drift forever in the freezing black. These are rogue planets, and they are one of the most haunting discoveries in modern astronomy. Unlike every planet in our solar system, these worlds are not bound by gravity to any star. They travel solitary paths through the interstellar void, untethered and invisible in the perpetual night. The formation of such a lonely existence is a story of cosmic violence. Most are likely born in the chaotic nurseries of young star systems, but a gravitational tug of war between giant planets can fling a smaller world out of its orbit, hurling it into the abyss like a stone from a sling. Some might even form on their own, directly from collapsing clouds of gas and dust, as failed stars that never gathered enough mass to ignite. Detecting something that emits no light of its own and floats in utter darkness is a monumental challenge. Astronomers use a clever trick called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity acts as a tiny lens, bending and briefly magnifying the star's light. That faint, telltale brightening, lasting perhaps just hours or days, is the only signature of a dark world silently crossing our line of sight. This method suggests a staggering truth. There may be billions, even trillions, of these nomads wandering the Milky Way, far outnumbering the stars themselves. The most chilling thought, however, is not their loneliness but their potential for hidden warmth. A large rogue planet with a thick insulating layer of ice and a rocky core heated by radioactive decay could maintain a vast global ocean beneath its frozen crust. In that eternal darkness, far from any starlight, geothermal vents on the ocean floor could provide both the energy and the chemistry needed for life to arise and persist. These dark, wandering worlds could be stealthy arcs carrying entire ecosystems through the galaxy, completely undetected from the outside. The idea transforms our search for life from a quest for sunlit Earths to a consideration of lightless internal abysses, suggesting that life may be far more adaptable and far more hidden than we ever dared to dream. While rogue planets wander in darkness, other celestial objects are launched into the void with unimaginable speed. Racing through the outer reaches of our galaxy are hypervelocity stars, cosmic projectiles ejected from the very heart of the Milky Way. One of the fastest ever detected is known as S5HVS1, a stellar bullet traveling at over 6 million kilometers per hour. At that staggering velocity, it is not merely orbiting the galactic center, it is escaping the Milky Way's gravitational grasp entirely, destined for the emptiness between galaxies. The engine behind this incredible launch is none other than Sagittarius, a star, the supermassive black hole that anchors our galaxy. The process is a gravitational slingshot of terrifying elegance. Imagine a binary star system, two stars locked in a mutual orbit, drifting too close to the black hole's event horizon. The immense tidal forces of Sagittarius, a star, can violently tear the pair apart. One star is captured, spiraling into an orbit around the black hole or being consumed entirely. The other, like a stone from a slingshot, is flung away at a significant fraction of the speed of light, recoiling from the interaction with enough energy to break free from the galaxy forever. We can trace the trajectory of these stellar outcasts directly back to the galactic center, a cosmic fingerprint of the violence that created them. Their fate is a lonely and cold one. They will streak across the galactic halo, leaving the light of the Milky Way's spiral arms behind as they cross into intergalactic space. There, they will travel for eons, their light growing faint, until they perhaps enter the domain of another galaxy billions of years from now, or simply burn out in the infinite cold. These stars are more than just runaway engines of fusion. They are living proof of the dynamic and often violent processes that shape galaxies from within, demonstrating that even the heart of our home can act as a catapult, launching its own children into the endless dark. This cosmic silence, despite a galaxy teeming with potential, leads us to one of the most profound questions in science. Enrico Fermi, a physicist helping to build the atomic bomb, posed it over lunch one day in 1950. With billions of stars older than our Sun, and the Milky Way itself being billions of years old, the math suggests intelligent life should have arisen many times over. Given enough time, a civilization just slightly more advanced than ours could colonize the entire galaxy. So, with the universe appearing so perfectly suited for life, where is everybody? This simple, devastating question is the heart of the Fermi paradox. The contradiction is staggering. Our galaxy contains hundreds of billions of stars, and most of those are now believed to host planets. Conservative estimates suggest there could be tens of billions of potentially habitable, Earth-like worlds in the Milky Way alone. Even if the odds of intelligent life emerging on any given planet are astronomically small, the sheer number of chances means we should not be alone. We should see evidence of cosmic engineering, hear their communications, or find their probes. Yet our telescopes and radio dishes have found nothing but a vast, unbroken quiet. This great silence is more puzzling than any signal we could receive. To resolve the paradox, scientists have proposed many unsettling solutions. One of the most discussed is the idea of a great filter. This theory suggests that somewhere between the initial conditions for life and the emergence of a galaxy-spanning civilization, there is an evolutionary or technological barrier so extreme that almost every species fails to cross it. The terrifying part is we do not know if we are behind the filter or still approaching it. Is the filter behind us something like the miraculous jump from non-living chemistry to simple, self-replicating life? Or is it still ahead, waiting to destroy us, perhaps in the form of self-annihilation through war or environmental collapse? or a dangerous technology we cannot yet control. Another possibility is the zoo hypothesis, which imagines that advanced civilizations are out there, but they have deliberately placed us in a kind of cosmic quarantine. They observe us from a distance, following a strict policy of non-interference to allow our species to develop naturally, much like we observe animals in a wildlife preserve. Or perhaps the truth is even stranger. Maybe intelligence as we understand it is a fluke, and most advanced life is so profoundly different, existing as planetary-scale consciousness or in forms of physics we cannot perceive, that we simply do not recognize their presence. They could be all around us, embedded in the fabric of space itself, and we lack the senses to notice. The silence, then, is not empty. It is filled with possibilities, each one a mirror reflecting our own hopes, fears, and profound cosmic solitude. It forces us to confront a humbling idea that either we are miraculously first, tragically alone, or blissfully unaware of the neighbors who have chosen to remain quiet. The eerie silence of the cosmos is sometimes broken not by a signal, but by an absence of light. In the constellation Cygnus, about 1,400 light-years away, a star named KIC 8462852, now famously called Tabby's star, performs a light show unlike any other. Discovered not by a team of professional astronomers, but by citizen scientists sifting through public data from the Kepler Space Telescope, this star's behavior defies easy explanation. Kepler's mission was to find planets by detecting the regular, gentle dips in starlight caused by an orbiting world passing in front of its sun. Tabby's star, however, does something radically different. Its light does not dip in a predictable, repeating pattern. Instead, it experiences dramatic, irregular dimming events, sometimes losing up to 22% of its brightness for days or weeks at a time, a blockage far too large to be a simple planet. If something passed between us and our own sun, blocking that much light, the object would have to be almost half the width of the star itself. The light curve graphs of this star look less like a tidy heartbeat and more like the frantic scribble of a seismograph during an earthquake, with deep, jagged troughs and a long-term, gradual fading that adds another layer to the puzzle. The immediate and most thrilling hypothesis was that we might be witnessing an alien megastructure. Specifically, scientists theorized about a Dyson swarm, a vast collection of energy-capturing satellites orbiting a star, constructed by a civilization harnessing its total power output. The irregular dips could be explained by a partially built, lopsided swarm of these constructs drifting in front of the star. While this idea captured the public imagination, science demanded more mundane, though no less fascinating, explanations. The leading natural theory involves a colossal swarm of comets, perhaps the debris from a shattered icy planet, encircling the star in a highly eccentric orbit. As this cloud of dust and fragments passes in front of Tabby's star, it would block light in chaotic, hard-to-predict ways. Other ideas point to intrinsic stellar activity, suggesting the star might be consuming a planet or that it is surrounded by a warped, dusty disk with large clumps of material. Years of intense observation have leaned toward dusty explanations, as the star dims more in blue light than in red, a signature of small particles scattering shorter wavelengths. Yet the definitive answer remains elusive. Tabby's star is more than a single mystery. It is a prototype. It exemplifies a new era of discovery where vast datasets and public collaboration can flag cosmic anomalies that challenge our categories. It teaches us that the universe is capable of engineering projects on a scale we can barely conceive, whether through natural astrophysics or, just possibly, through intelligence. The star's flickering light is a beacon, reminding us that sometimes the most profound questions are raised not by what we see, but by what we suddenly cannot. The profound quiet of the cosmos was broken for 72 seconds on a hot August night in 1977. At the Big Ear Radio Telescope in Ohio, a volunteer named Jerry Amon was reviewing a printout of data from a scan of the constellation Sagittarius. What he saw made him grab a red pen and circle a string of letters and numbers on the continuous feed, writing a single, emphatic word in the margin: "Wow." The signal was a powerful, narrowband radio burst at exactly 1420 MHz, a frequency that is naturally silent because it is protected by international agreement, reserved for listening to the universe. It came from a point near the star cluster Chi Sagittarii, rose to a peak intensity, and then faded away exactly as you would expect if a distant, focused beam swept across our fixed telescope. It bore all the hallmarks of an artificial, extraterrestrial origin, a perfect candidate for a signal engineered by intelligence. Yet, despite decades of pointed searches aimed at that same patch of sky, the signal was never heard again. It remains a solitary, brilliant flash in the cosmic record, a one-time event that has never been explained or replicated. The mystery of the WOW signal lies in its perfect, frustrating ambiguity. Its characteristics were ideal for what scientists call a technosignature, a signpost of technology, but its singularity defies confirmation. Natural explanations have been proposed, ranging from a comet's hydrogen cloud that was unknown at the time to a signal reflected off a piece of space debris. Yet none fit the data as neatly as that first thrilling interpretation. It stands as a ghost in the machine of our search for cosmic company, a tantalizing whisper that arrived, declared its presence with startling clarity, and then vanished forever into the static. This single event encapsulates the entire emotional arc of the search for extraterrestrial intelligence, a field defined by immense patience punctuated by moments of heart-stopping possibility. It teaches us that evidence may not be a continuous conversation, but a fleeting, enigmatic shout into the dark, leaving us to wonder for generations if we were ever truly heard. The silence of a single signal gives way to a motion that encompasses everything we can see. Across the cosmos, not just individual galaxies, but entire clusters of them are caught in a mysterious current, streaming together at impossible speeds toward a point on the edge of nothing. Astronomers call this phenomenon dark flow, and it is one of the most unsettling discoveries in modern cosmology. By studying the subtle distortions in the cosmic microwave background, the afterglow of the Big Bang, scientists mapped the motion of over 1,000 massive galaxy clusters. They expected to see the random, churning motions of local gravity like eddies in a river. Instead, they found a coordinated river itself. These colossal structures, each containing thousands of galaxies, are all moving in the same direction at speeds exceeding 2 million miles per hour. This is not the general expansion of the universe which pushes galaxies apart in all directions. This is a targeted flow, as if every cluster is being pulled by a single, unimaginable force. The problem, the true source of the mystery, is where that force is located. The pull is coming from a direction that lies beyond the boundaries of our observable universe. Whatever is exerting this gravitational tug exists in a region of space-time so distant that its light has not had time to reach us in the nearly 14 billion years since the cosmos began. It is an influence from the unseeable. This presents a direct challenge to one of cosmology's bedrock principles, the cosmological principle, which states that on very large scales, the universe is uniform and isotropic, meaning it should look the same in every direction and have no preferred center or direction of motion. Dark flow suggests a startling violation, a cosmic lopsidedness on the grandest possible scale. So what could possibly be massive enough to pull the entire visible universe? The leading and most mind-bending explanation points to the multiverse. The theory suggests that our universe is one bubble in a vast, frothing sea of other bubble universes, each with its own physical laws and dimensions. Dark flow could be the gravitational pull from one of these neighboring universes, a titanic structure just beyond the horizon of our own cosmic bubble, warping the fabric of space-time we inhabit. Another possibility is a colossal concentration of matter and energy from a region of our own universe that inflated away from us during the Big Bang, a remnant of primordial unevenness on a scale we can scarcely comprehend. Whatever the cause, dark flow is a ghostly hand from the void, a clue written in the motion of galaxies that the story of existence is far larger and far stranger than the chapter we call home. The ghostly pull of dark flow hints at structures beyond our sight, but our own cosmic neighborhood holds a frontier just as vast and unseen. Encircling our solar system is a spherical shell of frozen relics so distant it defines the very edge of the sun's gravitational influence. This is the Oort cloud, a theoretical reservoir of trillions of icy planetesimals, the leftover building blocks from the solar system's formation 4.6 billion years ago. Its inner edge is thought to begin roughly 2,000 times farther from the Sun than Pluto, and it stretches outward for an almost inconceivable distance, reaching perhaps halfway to the nearest star. To visualize this scale, if you shrank the entire solar system with its planets and orbits to the size of a coffee cup, the Oort cloud would be a sphere of icy dust roughly the size of a large house surrounding it. This immense distance means these objects are not truly in orbit around the Sun in the way planets are. They are more like dormant sentinels, barely bound by gravity, drifting in a perpetual deep freeze only a few degrees above absolute zero. Their existence, while not directly observed, is the only explanation for the behavior of long-period comets. These spectacular visitors, like the famous comet Hale-Bopp, arrive from random directions in the sky on orbits that take thousands, even millions, of years to complete. They cannot originate from the orderly plane of the solar system. They must come from this isotropic spherical shell. A passing star, a rogue planet, or the gentle tidal pull of the Milky Way itself can nudge one of these sleeping icebergs, sending it on a million-year fall into the inner solar system where the sun's heat transforms it into a blazing comet. The most staggering fact about this distant halo is its relationship to interstellar space. The outer boundary of the Oort cloud is not a clean line. It gradually thins out until the sun's gravity is too weak to hold onto these objects at all. This means the nearest star system, Alpha Centauri, is actually closer to us than the outermost members of our own solar family. The space between stars is not truly empty. It is subtly interlaced with the faint, far-reaching tendrils of stellar influence, a reminder that even in isolation, nothing in the galaxy is ever completely alone. The serene drift of the Oort cloud is a cosmic illusion masking a far more violent reality. Our galaxy is not a static island of stars, but a voracious predator growing larger by consuming its smaller neighbors. This process, known as galactic cannibalism, is how majestic spiral galaxies like our own Milky Way have achieved their grand scale over billions of years. The mechanism is a slow, gravitational feast. When a small dwarf galaxy ventures too close to a giant, the immense tidal forces of the larger galaxy begin to stretch and tear it apart. Stars are ripped from their orbits, scattering into long, shimmering rivers that slowly dissolve into the galactic halo. We can see the evidence of these ancient meals still swirling around us. The most prominent is the Sagittarius dwarf spheroidal galaxy, a tiny satellite that has been orbiting the Milky Way for billions of years. With each pass, our galaxy strips away more of its stars, drawing them out into vast, looping streams that now encircle the entire Milky Way like the rings of a tree, marking a timeline of consumption. Even now, astronomers are mapping new stellar streams, ghostly tendrils of stars all moving in unison against the random background of the galactic disk. These are the dissolving skeletons of galaxies long since devoured, their final structures not yet erased by time. This cannibalistic process is not just a relic of the past, it is the inevitable future. In approximately 4 billion years, the Milky Way will engage in its most spectacular merger yet, a head-on collision with our nearest large galactic neighbor, the Andromeda Galaxy. This will not be a violent crash of stars, for the vast distances between the mean direct stellar collisions will be exceedingly rare. Instead, it will be a majestic, slow-motion dance of gravity. Over billions of years, the two spiral structures will become gravitationally entangled, stretching and distorting each other's shapes, flinging stars into new, chaotic orbits. Eventually, they will settle into a single, enormous elliptical galaxy, often nicknamed Milky Way. The night sky from any surviving planet will be transformed, filled with a brilliant, diffuse glow of merged starlight, a permanent monument to the dynamic, ever-changing nature of galactic life. Our home is not a finished product, but an ongoing construction project built from the remains of countless smaller galaxies that came before. Galactic cannibalism reveals a universe in constant, violent flux, but some stellar corpses wield a power that makes even galaxy mergers seem gentle. Among the most terrifying objects in the cosmos is the magnetar, a city-sized cinder left behind by a supernova that concentrates a nightmare into reality. These are neutron stars, the collapsed cores of massive stars, crushed so densely that a single teaspoon of their material would weigh billions of tons. Yet their true horror lies not in their density, but in their magnetism. A magnetar possesses a magnetic field a quadrillion times stronger than Earth's, a force so incomprehensibly powerful it exists in a realm of physics we cannot replicate. If you were to venture within 1,000 miles of one, the field would be so intense it would literally pull you apart at the atomic level. The magnetic force would distort the electron clouds that hold your atoms together, effectively dissolving you into a stream of subatomic particles long before any other physical force could act. This is not science fiction. It is the direct consequence of a magnetic grip that warps the very fabric of empty space around it. The energy for this field comes from the star's unimaginably rapid spin and a turbulent, superconducting soup of particles in its interior, a dynamo of pure ferocity locked inside a sphere barely 20 kilometers across. The true danger of a magnetar, however, is not its static field, but when it cracks. These stars have crusts of iron nuclei locked in a rigid lattice, and as the unimaginable magnetic stresses build, that crust can fracture in a starquake. The release of energy is catastrophic. In a fraction of a second, the magnetar can unleash a gamma ray flare brighter than all the stars in our galaxy combined. We have felt their reach. On December 27, 2004, a magnetar named SGR 180620, located 50,000 light-years away in the constellation Sagittarius, unleashed such a quake. For 0.2 of a second, it released more energy than our Sun has emitted in the last 250,000 years. The pulse of radiation, traveling for 50 millennia, washed over our solar system. It was so powerful it actually compressed Earth's magnetic field on the day side, ionizing the upper atmosphere and disrupting long-range radio communications. Satellites in orbit were momentarily blinded, their sensors overwhelmed by the distant scream of a dying star. To be affected by an event that occurred when humans were first leaving Africa is a staggering demonstration of cosmic connectivity. A magnetar flare from a nearby star within just a few thousand light-years could potentially strip the ozone layer from our planet, triggering a mass extinction. They are cosmic weapons that fire at random, reminders that the universe is not only vast and beautiful, but capable of generating localized apocalypses with a shudder. The universe's most famous portrait is a lie. The Pillars of Creation, that breathtaking Hubble image of towering cosmic dust and gas where new stars are born, presents a scene of majestic permanence. Those colossal, light-year-high columns in the Eagle Nebula appear solid, eternal. Yet the truth is far more poignant. Roughly 6,000 years ago, a cataclysm unfolded nearby. A massive star, having exhausted its fuel, ended its life in a supernova explosion of unimaginable violence. The resulting shockwave, a wall of searing energy and stellar debris traveling at millions of kilometers per hour, would have slammed into those delicate pillars. To structures made of tenuous gas and dust, such an impact is an apocalypse. The blast would have shredded them, tearing the majestic towers apart atom by atom, scattering their material back into the interstellar void from which they coalesced. The pillars of creation, as we know and love them, are almost certainly already gone. We are gazing at a ghost. This haunting reality is a fundamental consequence of the finite speed of light. The Eagle Nebula is about 7,000 light-years away. The light showing us the intact, beautiful pillars left that nebula 7,000 years ago. The light carrying the news of their destruction, traveling from the same point, has only had 6,000 years to reach us. We are living in a 1,000-year gap between realities, a cosmic delay where we see a past that no longer exists. Every image from a deep space telescope is a historical document, not a live feed. We study the universe through a museum of light, where the most spectacular exhibits may have vanished eons before humanity first looked up. This time-lag nature of astronomy forces a profound shift in perspective. We are not passive observers of a static stage. We are archaeologists of the present, piecing together the life cycles of stars and galaxies from evidence that is always out of date. The ephemeral beauty of structures like the pillars underscores a universal truth. Change is the only constant, even on scales that seem to dwarf human conception. The nebula is not a monument, it is a moment. Its destruction is not an end, but a transformation, recycling its enriched material into the next generation of stars and planets. The light that will eventually bring us the news of this rebirth is already on its way, a future revelation traveling silently through the dark, waiting for its turn to tell us the next chapter of a story that is always already over. That museum of ancient light holds a flaw, a patch of sky that is profoundly and inexplicably cold. Within the faint, uniform glow of the cosmic microwave background, the fossilized light from the infant universe, there exists a region so much colder than its surroundings it defies standard cosmological models. This is the CMB cold spot, a colossal circular area in the constellation Eridanus where the temperature of the primordial radiation dips by about 70 microkelvins. While that number sounds minuscule on the near-perfect canvas of the early universe, it is a staggering anomaly, a bruise on the sky 500 times larger than a full moon. This isn't a simple statistical fluke, it is a feature that challenges our understanding of the cosmos's very first moments. One leading explanation is that it is a shadow cast by a supervoid, an enormous bubble of relative emptiness in the cosmic web. If such a void existed along our line of sight, photons from the CMB passing through it would lose a tiny amount of energy climbing out of its weakened gravitational well, a process known as the integrated Sachs-Wolf effect. This would make that region appear cooler to our telescopes. The search for this void, however, has yielded mixed results. While some surveys have found a sparser region of galaxies in that direction, its size doesn't seem sufficient to explain the profound coldness of the spot. The mismatch between the expected cause and the observed effect is the heart of the mystery. This discrepancy opens the door to a far more radical idea, one that ventures beyond our single universe. The cold spot could be a cosmic scar, the imprint of a collision between our universe and another bubble universe in the vast multiverse. In the theory of eternal inflation, our universe is one bubble in an endless, frothing sea of other universes, each with potentially different physical laws. If, during the universe's rapid inflationary phase just after the Big Bang, our bubble universe brushed against a neighboring one, the interaction could have drained energy from that contact zone. This would leave a distinct circular region in the CMB that is significantly colder, a permanent fingerprint of a reality beyond our own. The cold spot, therefore, is more than a curiosity. It is a cosmic Rorschach test. Do we see a rare but natural emptiness, a statistical outlier in an otherwise uniform cosmos? Or are we staring at the first tangible evidence of a multiverse, a shadow on the wall of our cave cast by a fire burning in another reality entirely. Its continued defiance of simple explanation makes it one of the most tantalizing puzzles in all of cosmology, a whisper from the dawn of time that may be telling us we are not alone in the ultimate sense, that our entire universe has neighbors. The concept of weather is utterly redefined on worlds beyond our own. While we complain of rain or heat, the atmospheres of many exoplanets host meteorological nightmares that make our most violent storms seem tranquil. Take the cobalt blue world known as HD 189733b, a gas giant orbiting perilously close to its star. Its azure hue comes not from oceans but from a hazy, silicate-rich atmosphere. Temperatures soar to nearly 1,000 degrees Celsius, hot enough to melt glass. Here, the wind does not whisper, it screams. Supersonic gusts, reaching speeds of 8,700 kilometers per hour, whip vaporized silicon and silica into a frenzied, sideways sandblasting of the planet. When conditions shift, these silicate particles condense into droplets of molten glass that rain sideways across the sky. A horizontal, scouring downpour that would shred any structure to atoms in seconds. This is not precipitation, it is planetary sandblasting on a global scale. Even more metallic horror awaits on WASP 76b, a tidally locked giant where one face permanently bakes under its sun and the other languishes in eternal night. The dayside temperature is so extreme, over 2,400 degrees Celsius, that metals like iron vaporize into the superheated atmosphere. Powerful planet-spanning winds then carry these clouds of atomic iron from the day side to the frigid night. As the iron-laden air crosses the terminator into darkness, it plummets in temperature by nearly 1,000 degrees. The iron condenses not into flakes but into droplets of molten metal, falling from the sky as a burning, liquid iron rain. Imagine standing on that dark, rocky surface, looking up to see not stars, but a glowing drizzle of incandescent metal, a perpetual, hellish forge raining from the heavens. These are not the only atmospheric aberrations. So-called hot Jupiters, gas giants orbiting searingly close to their stars, exhibit clouds unlike anything in our solar system. On worlds like Kepler 7b, astronomers have detected clouds not of water vapor but of vaporized rock. Silicates and other minerals, heated to a gaseous state, rise into the upper atmosphere only to cool and condense into droplets of liquid rock or dusty mineral particulates, creating permanent, high-altitude shrouds of molten stone. The weather forecast on such a world would be a single, unending statement: scorching heat with a chance of molten rock precipitation. These alien atmospheres demonstrate that the physics we know can combine in terrifyingly novel ways under extreme conditions, crafting skies of pure nightmare and proving that the universe's creativity is not limited to the serene and the beautiful. It has a profound capacity for the monstrously majestic. Far from the hellish skies of alien worlds, our own solar system holds a gravitational mystery in its frozen backyard. Beyond the orbit of Neptune, in a region known as the Kuiper Belt, thousands of icy objects drift in the deep cold. Astronomers expected their orbits to be randomly scattered, a gentle dispersion from the solar system's early days. Instead, they found a peculiar pattern. A handful of the most distant objects, those with elongated orbits taking them hundreds of astronomical units from the Sun, are mysteriously clustered. Their orbital paths are tilted in a similar direction, and their closest approaches to the Sun are grouped together on one side of the solar system. This is statistically bizarre, like finding several independently spinning tops that all happen to fall over pointing at the same corner of the room. The odds of this happening by random chance are astronomically low, suggesting an unseen force is herding them. This gravitational shepherd, according to the leading hypothesis, is a planet. Not a small, rocky world, but a potential giant, a so-called Planet 9. The theoretical world would be a cold behemoth, perhaps 5 to 10 times the mass of Earth, tracing a slow, monstrous orbit that could take between 10 and 20,000 years to complete a single journey around the Sun. Its immense gravity, acting from such a vast distance, would act like a hidden pendulum, gradually sculpting the orbits of these distant Kuiper belt objects into the aligned cluster we observe. The search for this phantom planet is a monumental game of celestial hide and seek. Its proposed orbit is so vast and its reflected sunlight so faint that spotting it is like trying to find a single, dim coal in the blackness of a cavern, using only the light from a match held at the cavern's entrance. Astronomers are methodically scanning the most likely patches of sky with the world's most powerful telescopes, looking for that telltale slow crawl of a dot against the fixed background of stars. The implications of finding it would be profound. It would rewrite the story of our solar system's formation, suggesting a dramatic past where giant planets jostled for position, potentially ejecting one entirely or flinging this hypothesized world into its distant, looping prison. For now, Planet 9 remains a ghost in the equations, a gravitational signature written in the paths of frozen rocks at the edge of everything we know. Its potential discovery would not just add a new planet to our charts, it would reveal that our own cosmic neighborhood still holds giant, ancient secrets waiting in the dark. Our own solar system's slow journey traces a grander circle than any planetary orbit. The Sun, with all its planets in tow, is not stationary at the center of the galaxy, but a passenger on a majestic, sweeping path around the Milky Way's core. One complete revolution of this cosmic carousel takes between 225 and 250 million Earth years. This immense span of time is known as a galactic year, the true clock by which our star measures its life. To understand this scale, we must compress Earth's entire history onto this new calendar. Our Sun formed roughly 4.6 billion years ago. In the language of the galaxy, that means it has completed only about 20 of these galactic orbits. Life on Earth provides a humbling perspective. Simple, single-celled organisms emerged perhaps 17 galactic years ago. The age of the dinosaurs began around 1 galactic year ago and ended just half a galactic year in the past. The entire saga of human civilization, from the first cities to the present day, has unfolded in the last few thousandths of a single galactic orbit. In the time it takes for our Sun to make one leisurely loop around the galactic center, continents have drifted into entirely new configurations, species have risen and fallen in countless cycles, and stars in other parts of the galaxy have been born and died. We measure our history in revolutions around our star, but our star measures its history in revolutions around a black hole. This cosmic clockwork forces a profound shift in perspective. All of recorded human achievement is less than a blink in the eye of the galaxy. Yet, within that blink, we have learned to measure the clock itself, to trace our path through the void and understand our place in this slow, beautiful, and utterly indifferent dance. The slow, majestic clockwork of the galaxy is built upon laws we believe are unbreakable. Yet at the heart of the most destructive objects in the cosmos, a fundamental rule of reality appears to shatter. This is the black hole information paradox, a puzzle so deep it threatens to unravel our understanding of physics itself. The conflict begins with two pillars of modern science that refuse to agree. On one side stands quantum mechanics, the rulebook for the very small. One of its most sacred principles is that information cannot be destroyed. Information, in this sense, is the complete quantum identity of every particle, its spin, its charge, its unique history. If you burn a book, the ash and smoke still contain, in principle, all the information needed to reconstruct every letter on every page. The information is scrambled, but it is not gone. On the other side stands general relativity, which describes gravity and the fabric of space-time. It gives us black holes, objects with gravity so intense that nothing, not even light, can escape their event horizon. For decades, physicists viewed black holes as the ultimate dead ends. If you throw a book, a car, or an entire star into a black hole, general relativity says that object's information is trapped forever behind the curtain of the event horizon, lost to our universe. This was troubling, but not yet a paradox. Then Stephen Hawking made a revolutionary discovery. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak a faint glow of thermal radiation, now called Hawking radiation. This radiation causes the black hole to gradually lose mass and over eons evaporate completely. Here is where the crisis erupts. Hawking's calculations indicated that this escaping radiation is purely thermal, like the heat from a stove. It carries no information about what fell into the black hole. It is random noise. So imagine our book falls into the black hole. The black hole eventually evaporates, leaving behind only this formless, featureless Hawking radiation. The book's specific information, the arrangement of its atoms, the words on its pages seems to have been erased from existence. According to quantum mechanics, this is impossible. Information must be preserved. According to Hawking's original work on black hole evaporation, it is not. Hence, the paradox. The universe appears to face an impossible choice. Either quantum mechanics is wrong, or our understanding of black holes is incomplete. Most physicists bet on the latter. The leading resolution to this nightmare is the idea that information is not lost inside the black hole, but is somehow encoded onto its event horizon, the surface that marks the point of no return. One compelling theory suggests that everything that falls in leaves a kind of holographic imprint on this two-dimensional surface, a fuzzy, scrambled record like a cosmic fingerprint. As the black hole evaporates via Hawking radiation, this encoded information is slowly and chaotically released back into the universe through subtle correlations in the radiation. The information was never truly gone. It was just transformed into a language we are only beginning to decipher. Solving this paradox is not an academic exercise. It is a necessary step toward a theory of quantum gravity, a single framework that can marry the world of the very small with the realm of cosmic gravity. The black hole information paradox is a screaming alarm that our current maps of reality are missing a continent. It tells us that even in the act of total destruction, the universe might still keep perfect, silent records. The conflict between quantum rules and cosmic destruction finds its parallel in a structure of such immense scale, it seems to break the rules of the universe itself. Known as the Hercules Corona Borealis Great Wall, this is not a physical barrier of stone or metal, but a titanic filament of galaxies, a thread in the cosmic web so vast it strains our fundamental understanding of the cosmos. Stretching for an estimated 10 billion light-years, it is one of the largest single structures ever identified in the observable universe. To grasp that scale, a beam of light, which can circle our entire planet 7 times in a single second, would need to travel for 10 billion years just to go from one end of this wall to the other. That is over a fifth of the observable universe's diameter. This immense ribbon of galaxy clusters and superclusters challenges a cornerstone of modern cosmology called the cosmological principle. This principle states that on sufficiently large scales, the universe should look roughly the same in every direction and be smooth, without any preferred locations or giant structures. It is the idea that the universe is homogeneous and isotropic, a cosmic assumption that allows us to apply our physics evenly across the vast expanse. The Hercules Corona Borealis Great Wall throws a wrench into that elegant idea. A structure of this magnitude should not exist according to our standard models of the universe's evolution after the Big Bang. There simply hasn't been enough time, given the age of the universe and the speed of light, for gravity to pull matter together over such an unimaginable distance. It is like stirring a cup of coffee and finding, instead of a uniform mixture, all the coffee grounds arranged into a single, perfect line that stretches far beyond the rim of the cup. The discovery of this wall and other similar giant structures like the Sloan Great Wall forces cosmologists to re-examine their models. It places a hard limit on how big things can theoretically get. These are not just curiosities, they are boundary markers, the universe showing us the upper ceiling of its own architectural potential. Their existence hints that the processes that seeded the universe with slight irregularities in the first fractions of a second after the Big Bang may have been more powerful or more uneven than we ever predicted. The wall stands as a silent, gargantuan question written across billions of light years, asking us if our maps of reality are complete or if we are still missing the true blueprint of creation. The universe's grandest structures are defined by the relentless pull of gravity, but sometimes the smallest push can create the deepest mystery. As the twin Pioneer spacecraft 10 and 11 completed their historic tours of the outer planets and sailed into the void, scientists tracking their radio signals noticed something deeply wrong. An unknown force was acting on the probes, a faint but persistent deceleration tugging them back toward the Sun. This was the Pioneer anomaly, a tiny deviation in their expected speed that haunted physics for decades. The numbers were minuscule but undeniable, equivalent to a deceleration of about 8.74 times 10 to the negative 10 meters per second squared. To put that in human terms, it was as if the spacecraft were experiencing a constant, gentle breeze blowing from the direction of the Sun, a breeze that shouldn't exist in the frictionless vacuum of space. For years, this anomaly fueled wild speculation. Had we discovered a flaw in Einstein's theory of general relativity? Was some unknown form of dark matter exerting a drag in the outer solar system? Or was it evidence of a new, long-range fundamental force? The mystery persisted because the Pioneer probes were ideal test subjects. Unlike later missions with complex, spinning reaction wheels and frequent thruster firings for stabilization, the Pioneers were simple spinners coasting smoothly on their way with minimal internal disturbance. This made their trajectory a pristine laboratory for measuring deep space physics, and the measurement was stubbornly off. The solution, when it finally came, was not found in the distant cosmos but in the spacecraft's own engineering. A team of researchers embarked on a monumental detective hunt, recovering decades-old design documents, telemetry data, and even fabricating replica components. Their conclusion was brilliantly mundane. The spacecraft were powered by radioactive thermoelectric generators, which produced heat as a byproduct of creating electricity. This heat radiated away from the spacecraft in all directions. However, because the Pioneers were designed with their main antennae always pointed back at Earth, the heat radiating from the rear of the craft away from Earth was slightly more efficient than the heat radiating from the front. This tiny asymmetry created a net photon thrust, a gentle push from the light and heat itself back toward the Sun. It was a minuscule thermal recoil, exactly the right amount to explain the anomalous deceleration. The Pioneer anomaly transformed from a potential physics-shattering discovery into a profound lesson in humility and precision. It taught us that to hear the faint whispers of the universe, we must first learn to silence the subtle hum of our own machinery. The greatest mysteries are not always out there in the dark. Sometimes they are riding along with us, hidden in the warm glow of our own ambition. The gentle push of escaping photons from our own spacecraft stands in stark contrast to the silent, unstoppable momentum of our farthest-reaching creation. Voyager 1 is no longer a probe within our solar system. It is a citizen of the galaxy. Launched in 1977, this small, nuclear-powered craft has traveled for over 46 years, covering a distance of more than 14 billion miles. In 2012, it crossed a fundamental boundary, the heliopause, where the outward pressure of the solar wind finally yields to the interstellar medium. Voyager 1 is now in the space between the stars, carrying with it the faint, fading heartbeat of human civilization. Its primary mission to study the outer planets was a spectacular success, but its ultimate purpose is far grander and more poetic. It is a message in a bottle cast into the cosmic ocean, designed to outlast not only its creators, but perhaps their very world. Attached to its side is a 12-inch gold-plated copper disc, the Voyager Golden Record. This is not a digital file, but a physical phonograph record, complete with a cartridge, a needle, and pictographic instructions on its cover for how to play it. It is a time capsule for eternity, curated by a committee led by Carl Sagan. The record contains the sounds of Earth, the crashing of waves, the songs of birds, the heartbeat of a human, and greetings in 55 languages, from ancient Akkadian to modern English. It carries an hour of encoded brainwave readings from a person in love, and 115 images etched into the analog medium, depicting our planet, our anatomy, our science, and our daily life. The music selection is a breathtaking mosaic of human expression, from Bach and Beethoven to Chuck Berry and Blind Willie Johnson, from a Navajo night chant to a Senegalese percussion piece. It is a portrait of a species at its most hopeful, choosing to represent itself not with declarations of war or borders, but with curiosity, art, and a desire to connect. Yet this ambitious act of cosmic communication is shadowed by a quiet, inevitable truth. Voyager 1 is running out of time. Its power comes from 3 radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity. That plutonium has a half-life, and with each passing year, the output dwindles. To conserve the remaining energy, engineers have begun the difficult process of turning off its scientific instruments one by one. By around 2025, there will no longer be enough power to run any single instrument. Sometime after 2030, all systems will go dark. The faint blue dot of its transmitter will fall silent forever, but Voyager itself will not stop. It will continue its journey, a silent, dark bullet of aluminum and circuitry. In about 40,000 years, it will drift within 1.6 light-years of a star in the constellation Camelopardalis. It will not be aimed at any star in particular, for its trajectory was set by planetary flybys, not a chosen destination. It will simply wander, a monument to a civilization that once looked up, built a machine, and flung a piece of itself into the future. Long after our cities have turned to dust and our sun has grown cold, Voyager 1 and its twin, Voyager 2, will still be sailing through the starry night, carrying a golden whisper of who we were, waiting in the interstellar dark for a finder who may never come. The silent voyage of our artifacts into the void mirrors a slow-motion departure happening right in our sky. Our own moon is leaving us. Each year, the lunar companion that has inspired myth and guided humanity for millennia drifts about 1.5 inches farther from Earth, a retreat driven by the relentless mechanics of tides. This gentle but constant recession is a side effect of Earth's rotation. The gravitational pull of the moon creates a bulge of water in our oceans, the tidal bulge. Because Earth spins faster than the moon orbits, this watery bulge is dragged slightly ahead of the direct line between the two worlds. This offset bulge then pulls gravitationally on the moon, giving it a tiny kick of energy that pushes it into a slightly higher, slower orbit. In turn, the moon's gravity pulls back on that bulge, acting as a brake on Earth's rotation, gradually slowing our day. It is a cosmic exchange of energy, a gravitational transaction written in the rock of our world and the orbit of our satellite. The current rate seems insignificant, a sliver of distance over a human lifetime, but project this slow creep across the deep future and the consequences transform our world. In about 600 million years, the moon will have drifted far enough that it will no longer be able to completely cover the sun's disk as seen from Earth. The breathtaking coincidence of size and distance that creates a perfect total solar eclipse, with the sun's fiery corona shimmering around the black lunar disk, will be a phenomenon of the past. Eclipses will only ever be annular, with a ring of brilliant sunlight forever visible around the moon's silhouette. A fundamental celestial spectacle, one that has sparked awe, fear, and scientific discovery throughout history, will simply vanish from the experience of any future Earthlings. The longer-term changes are even more profound. As the Moon continues to recede, its tidal braking will keep slowing Earth's rotation. Our days will grow longer, stretching from 24 hours to 25, then 30 and beyond. The rhythm of life itself, evolved under the pulse of our current spin, would have to adapt to a fundamentally different cycle of light and dark. The Moon itself would appear smaller and smaller in the sky, its gentle light dimming with distance. This is not a story of sudden loss, but of a gradual, inevitable uncoupling. The Moon was born from a cataclysmic collision, and it will depart with a silent, inch-by-inch farewell, changing the very face of the heavens and the beat of our planet's heart over spans of time that dwarf human history. The Moon's slow farewell is a gentle reminder that even our most fundamental cosmic relationships are temporary. Yet this pales before a discrepancy in physics so vast it has been called the worst theoretical prediction in the history of science. We call it the vacuum catastrophe, and it reveals a chasm in our understanding of reality so deep it threatens to swallow our theories whole. At its heart is a simple, terrifying number. According to our best theories of quantum mechanics, the vacuum of space should not be empty. At the tiniest scales, it is a seething foam of virtual particles constantly blinking in and out of existence. This quantum frenzy should imbue every cubic centimeter of the universe with a colossal amount of energy, a background hum of vacuum energy. When physicists calculate this theoretical energy density, they arrive at a number. When astronomers measure the actual energy density of the cosmos, which we call dark energy, they get a different number. These two numbers should be the same thing, describing the energy of empty space. They are not. The theoretical prediction is larger than the observed reality by a factor of 10 to the power of 120. To grasp the absurd scale of this error, imagine predicting the weight of a single proton. Now imagine your prediction was that this proton weighed more than the entire observable universe. Your error would still be unimaginably smaller than the vacuum catastrophe. It is a failure of prediction so spectacular, it is less a mistake and more a scream from the foundations of physics that something is fundamentally wrong. This is not a minor calibration issue. It suggests that either our understanding of quantum field theory is missing a crucial piece of mathematics that cancels out almost all of this vacuum energy, or our theory of gravity, Einstein's general relativity, breaks down on cosmic scales. Perhaps the vacuum energy is real, but something else, some unknown force or structure, is counteracting it almost perfectly, leaving behind only the faint whisper we detect as dark energy. The embarrassment for physicists is profound. It means that one of our two most successful theories of reality, when asked a basic question about the energy of nothing, produces an answer that is wrong by a margin greater than the number of atoms in the universe. The vacuum catastrophe stands as a silent monument to our ignorance, a humbling reminder that for all our maps and equations, the true nature of the void remains one of the universe's best-kept secrets. While the vacuum's energy remains a ghost in our equations, another invisible force sculpts the galaxy in plain sight. We move through a magnetic universe, one where the space between stars is not empty but threaded with immense, organized fields of force. These galactic magnetic fields are the silent architecture of the Milky Way, a web of influence as real as gravity, yet unseen by human eyes. They do not originate from simple bar magnets, but are generated by the churning motions of ionized gas or plasma within the galactic disk, a process akin to a colossal, slow-motion dynamo. The fields stretch for thousands of light years, aligning along the spiral arms, creating a cosmic fingerprint of order within the apparent chaos of interstellar space. Their strength is deceptively subtle, millions of times weaker than a common refrigerator magnet, but their scale is everything. Encompassing the entire galaxy, this diffuse magnetic grip exerts a gentle, pervasive influence on almost every process within it. One of their most crucial roles is as a regulator for cosmic rays, the high-energy atomic fragments that scream across the galaxy at nearly the speed of light. As these charged particles, mostly protons and electrons, journey through space, the galactic magnetic fields bend their paths. Instead of traveling in straight lines, cosmic rays spiral along the invisible field lines, corkscrewing through the void. This turns what would be a deadly, direct barrage into a diffuse, chaotic haze. The magnetic web acts as both a shield and a trap, confining these particles to the galaxy for millions of years, bouncing them back and forth until they eventually leak out or lose their energy. Without this magnetic maze, the intensity of cosmic radiation reaching planetary surfaces could be profoundly different, potentially altering the very conditions for life. These fields are also master sculptors in the nurseries of stars. Giant clouds of molecular gas, the raw material for new suns, are permeated by magnetism. As gravity tries to collapse a cloud to form a star, the magnetic field resists, providing a supporting pressure that can slow or even halt the process. It is a cosmic tug of war between collapse and containment. For a star to be born, the cloud must somehow shed its magnetic influence, often through a slow process called ambipolar diffusion, where neutral gas slips past the ionized particles locked to the field lines. This magnetic friction dictates the pace and efficiency of star formation, ensuring it is a stately, controlled process rather than a sudden, galactic-wide collapse. In this way, the invisible fields set the rhythm for the birth of new light across the Milky Way. But how do we map something we cannot see? We listen to the light. As starlight travels through the interstellar medium, dust grains aligned by the magnetic fields polarize the light, causing its waves to vibrate in a preferred direction. By carefully measuring this polarization from thousands of stars, astronomers can trace the orientation of the magnetic fields across vast distances, painting a picture of the galaxy's hidden skeleton. Recent maps from missions like Planck have revealed a startling complexity, with fields not only following the spiral arms but also looping and twisting in unexpected ways, suggesting a dynamic and turbulent magnetic life within the galactic disk. This hidden dimension, once thought to be a minor detail, is now understood as a fundamental component of galactic ecology, an invisible hand that guides the birth of stars, the journey of radiation, and the very structure of our cosmic home. Even the magnetic skeleton of our galaxy cannot prepare you for the geometric perfection waiting in the constellation Monoceros. There, surrounding the dying binary star system HD 44179, is a nebula that looks less like a cosmic cloud and more like a piece of divine geometry. Astronomers call it the red rectangle, and it is one of the most precisely structured objects ever discovered in the heavens. Through the lens of a powerful telescope, it appears not as a chaotic, blooming sphere of gas, but as a stunning, nested series of rectangles and a vivid X-shape glowing with a deep, ruby-red hue. This is not an artist's rendering or an optical illusion. It is the real, observed structure of a stellar system in its final act, and its symmetry is a direct clue to the violent ballet happening at its heart. The secret lies in the central dance of two stars. One is a post-asymptotic giant branch star, a luminous core left behind after a sun-like star has puffed away its outer layers. It orbits in a tight embrace with a smaller, hotter companion. As the primary star sheds its atmosphere in a slow, dense stellar wind, the gravitational influence and radiation from the smaller star sculpt that outflow into two opposing cones, like the beams from twin lighthouse beacons. Because we view this system almost perfectly edge-on, looking directly at the side of these cones, their walls appear as two intersecting lines forming that unmistakable X. The nested rectangular appearance comes from abrupt pauses or changes in the mass loss rate of the dying star over time. Imagine blowing a steady stream of smoke rings, then pausing, then blowing another set. If those rings expanded outward and were sliced in half by our line of sight, they would create the illusion of stacked boxes. That is precisely what we see in the red rectangle, layers of history frozen in expanding gas. The intense red color is another signature of this unique environment. It comes from a phenomenon known as extended red emission, a mysterious luminescence likely caused by complex carbon molecules, perhaps even the building blocks of future organic compounds, being excited by the harsh ultraviolet light from the hot companion star. This nebula is more than a cosmic curiosity, it is a laboratory. It demonstrates how binary star interactions can impose breathtaking order on the chaos of stellar death, creating temporary monuments of gas and dust that will, over thousands of years, dissipate and seed the interstellar medium with the very elements needed for new stars and planets. In its sharp angles and glowing red lines, we see the universe not as a random painter, but as a precise engineer following hidden blueprints written in gravity and light. The geometric beauty of a dying star's nebula is a fleeting masterpiece, but our own star has a far more destructive final act written in its core. The Sun, the steady anchor of our lives, is a middle-aged star currently in the most stable phase of its existence, the main sequence. For about 4.6 billion years, it has been fusing hydrogen into helium in its core, releasing the light and warmth that made life on Earth possible. This peaceful era is temporary. In roughly 5 billion years, the hydrogen fuel in the Sun's core will finally be exhausted. With no more fusion to push outward against gravity, the core will begin to contract and heat up dramatically. This heat will ignite a shell of hydrogen burning around the now inert helium core, causing the Sun's outer layers to expand at a terrifying rate. Our star will swell into a red giant, its radius ballooning to perhaps 200 times its current size. From the perspective of a future Earth, the sky will transform into a nightmare of beauty. The Sun will first grow into a monstrous, dull red orb, swallowing the orbits of Mercury and Venus whole. Our world will be on the very edge of this expanding inferno. The oceans will boil away, the atmosphere will be stripped by the solar wind, and the crust itself will melt into a global sea of magma. The once blue planet will become a scorched, lifeless cinder, orbiting inside the outer atmosphere of its own dying star. This is not a speculative fate, it is the inevitable consequence of stellar physics. After a relatively brief period of perhaps 1 billion years in its red giant phase, the Sun will become unstable. It will pulse violently, ejecting its outer layers into space in a series of magnificent, gentle eruptions. This ejected material will form a vast, glowing planetary nebula, a final shroud of gas and dust illuminated by the tiny, intensely hot core left behind. That core, no larger than Earth but containing about half the original mass of the Sun, will be a white dwarf. A single sugar cube-sized fragment of this degenerate stellar cinder would weigh as much as an elephant on Earth. This Earth-sized ember will be unimaginably dense and hot, initially glowing with a fierce white heat. But with no internal fusion to sustain it, it will slowly, over trillions of years, cool and fade to a black dwarf, a cold, dark crystal of carbon and oxygen adrift in the galaxy. The solar system we know will be unrecognizable. The inner planets will be gone, consumed or vaporized. The outer planets from Jupiter outward may survive, though their orbits will have shifted outward as the Sun loses mass. Their icy moons, warmed by the red giant's heat, could temporarily host liquid water oceans beneath their surfaces, creating fleeting oases in a system whose center has died. This timeline stretches far beyond human comprehension, yet it is as certain as the laws of physics. The Sun's story is a reminder that stability is an illusion granted by a temporary balance of forces. Our entire world, every mountain, every ocean, every memory, exists only because of a fragile, burning reaction at the heart of a star that one day will gently and utterly erase it all. This cosmic clockwork, the steady expansion that carries galaxies apart, is the very heartbeat of the universe. Yet our most precise tools for measuring its pulse are now giving us two different, stubbornly incompatible heartbeats. This is the Hubble tension, a growing crisis at the very foundation of cosmology that suggests something fundamental in our map of reality is wrong. The problem is deceptively simple. We have two primary ways to measure how fast the universe is expanding, a number called the Hubble constant. The first method uses the cosmic microwave background, the afterglow of the Big Bang, as a pristine snapshot of the infant universe. By analyzing the subtle patterns in this ancient light with exquisite precision, satellites like Planck can calculate what the expansion rate should be today, based on our standard model of cosmic evolution. The second method measures the expansion directly in our local, modern universe. Astronomers use so-called cosmic ladders, observing pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1a supernova. These are standard candles, objects whose intrinsic brightness we know, allowing us to gauge their distance accurately. By comparing their distance to how fast they are moving away from us, we get a direct local measurement of the expansion rate. Both methods are incredibly sophisticated, backed by Nobel Prizes and decades of refinement. The trouble is, they disagree. The local measurements consistently give a faster, more frantic expansion rate than the pristine prediction from the early universe. The discrepancy is not large, only a few percentage points, but it is far beyond the margin of error for either technique. It is a persistent, stubborn gap that has only widened as our instruments have grown sharper. This is not a minor calibration issue, it is a direct contradiction. Imagine using two different state-of-the-art thermometers to take your temperature. One, based on the chemistry of your birth, says you should have a normal fever. The other, placed on your forehead right now, says your fever is significantly higher. Both cannot be correct, so what does this mean for our understanding of the cosmos? The tension points to one of three unsettling possibilities. First, there could be unknown systematic errors in one or both measurement methods, some subtle flaw we have not yet uncovered despite intense scrutiny. Second, and more thrilling, it could mean our standard cosmological model, the lambda-cold dark matter model, is incomplete. This model is the backbone of modern cosmology, describing a universe made of ordinary matter, and dark energy. The Hubble tension could be the first hard evidence that one of these ingredients is not what we think. Perhaps dark energy is not a constant but evolves over time, strengthening in the modern universe to drive a faster expansion. Maybe dark matter has properties we have not accounted for, or there is an entirely new particle or field influencing the cosmos. The third, most profound possibility is that we are seeing the fingerprints of new physics, a fundamental law of nature that operates differently on the scale of the entire universe than it does in our local galactic neighborhood. Each potential solution sends shockwaves through our understanding. If the tension is real and not an error, we are standing at the edge of a revolution in physics, peering into a crack in our most successful model of the universe. The Hubble constant is not just a number, it sets the age, size, and ultimate fate of everything. To have it in dispute is to have the very timeline of existence called into question. This quiet disagreement between the ancient light and the modern stars is perhaps the most important unsolved problem in cosmology today, a whisper from the data that the universe still has profound, foundational secrets to reveal. This quiet disagreement over cosmic expansion is a modern puzzle, but our own galaxy holds evidence of a far more violent and recent outburst. Rising from the heart of the Milky Way, two colossal bubbles of pure energy stretch for 25,000 light-years each, one north and one south of the galactic plane. These are the Fermi bubbles discovered in 2010 by the Fermi Gamma Ray Space Telescope, and they are a pair of the most gigantic and enigmatic structures in our entire sky. Imagine two titanic, symmetrical balloons, each one towering over the galactic center, glowing with the most energetic form of light in the universe. They are invisible to our eyes, detectable only by the high-energy gamma rays that scream from the particles trapped within them. The scale is almost incomprehensible. If we could see them, they would span over half the visible night sky, a ghostly hourglass of ferocious power with our galaxy's delicate spiral disk pinched at its waist. Their very existence is a signpost of a cataclysm, a monumental explosion or eruption that happened in our galactic backyard relatively recently in cosmic terms. The leading suspect for the architect of this violence is none other than Sagittarius, a star, the supermassive black hole that sleeps at our galaxy's core. The most compelling theory is that several million years ago, this sleeping giant woke up for a feast. A massive cloud of gas, or perhaps a star that strayed too close, was torn apart by the black hole's gravity. As the doomed material spiraled into the accretion disk, it didn't just vanish quietly. A fraction of it was channeled by the black hole's immense magnetic fields and spun into two opposing relativistic jets, screaming outward perpendicular to the galactic disk. These jets, traveling at a significant fraction of the speed of light, would have punched through the halo of the Milky Way, inflating these giant bubbles of hot gas and accelerating particles to near light speeds. As these particles collide with the slower-moving gas and light within the bubbles, they generate the furious gamma-ray glow we detect today. It is a fossil of a black hole's lunch, a burp of cosmic proportions that left a permanent scar on our galaxy's structure. But there is another, equally dramatic possibility. The bubbles might not be the work of the black hole alone, but the combined fury of a starburst. In this scenario, a wave of intense star formation occurred near the galactic center millions of years ago. Hundreds of massive stars would have been born, lived their short, violent lives, and exploded as supernova in a rapid chain reaction fireworks display. The combined energy of all these explosions could have blown a giant bipolar superwind out of the galactic disk, carving out the cavities and filling them with energetic particles. This would make the bubbles a testament not to a single monster's appetite, but to the coordinated fury of stellar birth and death on an epic scale. Distinguishing between these two origins is an active frontier of research. The bubbles are not empty, they have structure and edges, and they emit other wavelengths of light like X-rays and radio waves that provide clues to their temperature and composition. Current observations lean toward the black hole jet model, as the bubble's sharp edges and symmetrical alignment with the galactic center fit that story neatly. Yet the truth may involve both forces, a collaboration between a feasting black hole and a frenzy of stellar explosions. The Fermi bubbles remind us that our galaxy is not a serene, stable pinwheel. It is a dynamic engine capable of colossal, episodic eruptions that reshape its very halo. We live in the quiet aftermath of one such eruption, its magnificent, silent structures towering over us, a permanent monument to the latent power slumbering at the heart of our galactic home. Even the violent structures carved by our galaxy's black hole obey a single, shared reality. But at the quantum edge of physics, reality itself splinters based on how you move through it. This is the Unra effect, a prediction from quantum field theory so strange it suggests the vacuum of space is not an objective emptiness, but a personal experience. According to this theory, an observer floating peacefully in empty space, an inertial observer, will detect nothing but a cold, perfect vacuum. Yet, an observer undergoing constant, violent acceleration, like the crew of a hypothetical starship with its engines permanently at full thrust, will perceive something utterly different. They will find themselves immersed in a warm bath of particles, a thermal glow rising from the void itself. For them, the vacuum is not empty, it is a sea of heat. This is not a matter of instrument error or illusion, but a fundamental shift in what constitutes reality for the accelerating observer. The particles they detect are real, with measurable energy and effects. The easiest way to grasp this is through a stark analogy. Imagine two astronauts separated in the void. One, Alex, shuts off their engines and simply drifts. The other, Sam, engages a powerful, constant acceleration, pushing ever faster. From Alex's perspective, Sam is the one moving, receding into the distance. But from Sam's cockpit, the instruments tell a different story. Sam's ship is not just moving, it is constantly interacting with the quantum foam of the vacuum in a new way. The relentless acceleration causes the ship's detector to become coupled with what are called virtual particles, the fleeting pairs of particles and antiparticles that quantum mechanics says constantly pop into and out of existence. For the inertial Alex, these pairs annihilate each other too quickly to be detected. But Sam's acceleration effectively stretches the fabric of space-time around the ship, preventing the pairs from recombining. One particle of the pair falls behind, unable to catch up to the accelerating ship, while its partner is swept along. To Sam, that trapped partner appears as a real, detectable particle arriving from the void. Since this happens countless times all around the ship, the result is not just a few random particles, but a uniform, warm glow of radiation. The temperature of this ghostly heat bath is directly proportional to the acceleration. A gentle, constant one-gravity acceleration would produce an unrut temperature of only about 4 trillionths of a degree above absolute zero, utterly undetectable with current technology. But the principle is what shatters our intuition. To create a noticeable warmth, an observer would need to accelerate at a truly monstrous rate, something on the scale of a quintillion times the force of Earth's gravity. At that horrific acceleration, the vacuum would appear to boil with particles, a searing plasma of quantum noise. This effect reveals a profound and unsettling truth about our universe. There is no single, privileged frame of reference that defines what is real. The very particles that constitute reality are not absolute fixtures, but relative phenomena dependent on the state of motion of the one who is looking. It tells us that the quiet, empty space we take for granted is a perspective, not a fact. The Unruh effect is a direct cousin to the Hawking radiation that evaporates black holes, both arising from the same quantum principles applied to different kinds of horizons, one created by gravity, the other by motion. It forces us to ask a deeply philosophical question. If reality is truly this fluid, what other fundamental aspects of our existence are merely artifacts of our particular, unaccelerated path through the cosmos? The fluidity of reality itself suggests that life, in all its forms, may be far more adaptable than we ever conceived. This brings us to a final, profound speculation that ties our cosmic journey back to our own origins. Could the spark that ignited life on Earth have arrived here from the depths of interstellar space? This idea, known as panspermia, proposes that the basic ingredients for biology, or even dormant microorganisms, can travel between planets and star systems, hitching rides on asteroids, comets, or cosmic dust. It is not a claim that aliens seeded our world with complex creatures, but a humbler, more plausible suggestion that the universe may be a vast, interconnected nursery, sharing its raw materials freely across the light years. The evidence for this cosmic sharing begins with the chemistry of space itself. Telescopes have detected a rich soup of organic molecules in giant molecular clouds, the same nurseries where stars and planets are born. We have found complex carbon-based compounds, including amino acids and sugars, in the spectra of these clouds and within meteorites that have fallen to Earth. The Murchison meteorite, which landed in Australia in 1969, contained over 90 different amino acids, many of which are used by life on our planet. These are not contaminants, they are probiotic chemicals formed in the harsh environment of space, proving that the universe is inherently capable of manufacturing life's building blocks long before a planet even forms. The journey for these molecules, however, is a harrowing one. To travel from one star system to another, they would need to survive the extreme cold and radiation of interstellar space, the violent heat and shock of planetary impact, and the brutal re-entry through an atmosphere. Yet, experiments have shown that some hardy bacteria, like certain species of Deinococcus, can survive for years in the vacuum of space when shielded within rock. A meteorite large enough could provide a protective cocoon for such dormant life during an interstellar voyage. The mechanism for this grand dispersal is written in the violent history of our own solar system. During the late heavy bombardment over 4 billion years ago, countless asteroids and comets pummeled the inner planets. These impacts were so powerful they could have ejected fragments of the early Earth or Mars into space. Some of these rocks, carrying any primitive life that may have existed, could have been flung out of the Sun's gravitational grip entirely, becoming interstellar travelers. Conversely, rocks from another planetary system could have been captured by our Sun's gravity and delivered to a young, receptive Earth. This turns the concept of a planet's biosphere from a closed, isolated garden into a potential node in a galactic network. If panspermia is true, then life on Earth may not be native. Our most distant ancestor, the last universal common ancestor or LUCA, that single-celled organism from which all life on this planet diverged, might itself have had extraterrestrial origins. Its precursors could have formed in the disk of dust around a young star elsewhere in the galaxy, were delivered here by a fortunate impact, and found in Earth's warm, watery environment the perfect conditions to awaken and thrive. This does not answer the deeper question of how life began in the first place. It simply moves the laboratory from a shallow tide pool on early Earth to the vast chemistry set of the galactic disk. The implications are staggering. If life can hop from one world to another, then it could be far more widespread in the galaxy than we think. A single genesis event on a single world could, over billions of years, spread its progeny to countless other planets via this natural, rocky spacecraft. Entire planetary systems could be biologically related, sharing a common cosmic ancestry. We would not be alone in the universe, we would be family, separated by immense distances but connected by a shared lineage written in our DNA and delivered on a voyage of rock and ice. This final fact reframes our entire search. We are not just looking for other life out there, we might be looking for our own long-lost cousins, scattered by the gentle, relentless tide of gravity and time. From the possibility of our own cosmic ancestry to the fluid nature of reality, this journey has revealed a universe that is not a silent, empty stage, but a living, breathing arena of impossible wonders. Each of these 30 facts is a crack in the ordinary, a glimpse into a cosmos that operates on scales and with a creativity that continuously defies our expectations. We have stood at the edge of voids so vast they should not exist, witnessed stars flung from the galaxy like stones from a sling, and confronted mysteries that pull at the very fabric of our physical laws. These are not just curiosities, they are signposts. They point to a reality far stranger, more dynamic, and more interconnected than the simple, static night sky often suggests. They speak of a universe where diamonds form entire worlds, where magnetic skeletons sculpt the birth of stars, and where the quietest emptiness holds the potential for both infinite heat and the seeds of life itself. This tapestry of the bizarre underscores 3 profound truths about our place in the cosmos. First, mystery is not a sign of our failure, but the universe's deepest nature. From the cold spot to the Hubble tension, the gaps in our knowledge are not empty spaces. They are the frontiers of discovery, the places where the next revolution in understanding awaits. Second, scale is the ultimate perspective shifter. Our human lives are measured in decades, but the universe operates in galactic years and on distances where light itself becomes a slow traveler. This scale does not diminish us, it liberates our imagination to conceive of processes and entities beyond our earthly experience. Finally, and perhaps most importantly, these facts humbly illustrate the limits of our current knowledge. The greatest lesson of modern astronomy is not how much we have figured out, but how much remains wondrously, thrillingly unknown. The universe is not a puzzle to be solved, but a story to be explored, one bizarre chapter at a time. So, as we return from the edges of voids and the hearts of dying stars, we turn the question to you. Which of these 30 facts reshaped your view of reality the most? Was it the ghostly pull of dark flow from beyond our universe, the silent departure of our moon, or the haunting possibility that we are all children of the stars? Let us know in the comments below. Share which cosmic truth left you in awe. If this journey through the strange and wonderful has sparked your curiosity, be sure to like this video and subscribe. There are always more mysteries waiting in the dark, and together we can keep exploring them.